In this video, we're going to get some practice identifying wholes and vertical asymptotes and also evaluating some infinite limits. So here for this example, I want to describe the behavior of the function at each zero of the denominator. We're going to use plus or minus infinity when it's appropriate. And at any vertical asymptotes, I want to find the left and the right hand limits. So the first thing I need to do before I can do anything else is I need to find the zeros of the denominator. So here my function, I've got f of x equals x minus 3 over x squared minus 4x plus 3. If you can, I definitely want to go ahead and factor that. My numerator I can't do anything with, so we've just got x minus 3. In my denominator, if I think about two numbers that multiply to be 3, add to be negative 4, that would be negative 3 and negative 1. So we've got x minus 3 divided by x minus 3 over x minus 1. And because we have that common factor of x minus 3 in both our numerator and our denominator, we can go ahead and cancel that common factor. So that means our simplified function here is now 1 divided by x minus 1. So what I first want to do is find those zeros of the denominator. So anything that's left over, I'm going to take that x minus 1, set it equal to 0, and solve that equation. So here I end up with x equals 1. And if that factor does not cancel, if we're left over with it, that means that we have a vertical asymptote at x equals 1. So we're going to have to do a little bit more work with that. And we'll come back to that in just a moment. But we actually have another zero of the denominator. We canceled a zero of the denominator right there. Now, we canceled it and it worked out nicely for us, but it's still a zero of the denominator. So I'm still going to need to take that canceled factor of x minus 3 and set it equal to 0 and solve that equation. So here when I do that, I end up with x equals 3. Because that factor canceled from our numerator and our denominator, that means instead of having a vertical asymptote at x equals 3, we have a hole in our graph at x equals 3. So here we've got two different zeros of the denominator and two different behaviors. We've got a hole at x equals 3. We've got a vertical asymptote at x equals 1. The other thing that I wanted to do here in this problem is I wanted to find the left and the right hand limits at any vertical asymptotes. So our only vertical asymptote we have here is x equals 1, so I want to look at, okay, let's look at limits as x approaches 1. We'll start from the left-hand side just because of our function f of x. And what we can do is we can actually use this simplified version of our function, 1 divided by x minus 1. So, okay, let's look at limit as x approaches 1 from the left of 1 divided by x minus 1. Now, if we tried to just take 1 and plug it into our function, we'd end up with 1 over 1 minus 1, gives us 1 divided by 0. So that's not going to work for us. But we do know some really helpful information here. We know that we have a vertical asymptote at x equals 1. What this means is that our limit is either going to be positive infinity or it's going to be negative infinity, because that's how a vertical asymptote is defined. The left and the right side limits have to be either positive infinity or negative infinity. So if we wanted to just guess, we've got a 50-50 shot. We know it's one of those two. One thing that we can do to help us, because obviously we don't want to just guess, we want to get the right answer, is I'm going to take a number that's close to 1 on the left-hand side. So remember, we're looking at the left-handed limit here. I'm going to take a number that's very close to 1 on the left-hand side. So I'm going to take, how about x equals 0.9. That's very close to 1, and it's on the left-hand side. I'm going to take that number and plug it into my function. So, okay, if we plug that into our function, we'll have 1 divided by 0.9 minus 1. And because we said earlier that our limit is either going to be positive infinity or negative infinity, all I really care about is the sign right now. Because I chose a number that's so close to 1, really what I care about is the sign. Is this number going to turn out to be positive, or is this number going to turn out to be negative? So 1, I might look at that numerator and say, you know what, that's just a positive number. We're just going to say that's positive. In our denominator, 0.9 minus 1, if I subtract those two, I'm going to end up with a negative number. So I have a positive divided by a negative. And when I take a positive divided by a negative, I'm going to end up with a negative number. So we said our limit was either positive infinity or negative infinity. We had to figure out which one. Here in this case, it's going to be negative infinity, because when we take a number that's close to 1 on the left-hand side, we're going to get a very large negative number. So for the left-hand limit, we would say that this is equal to negative infinity. And it's because of that negative sign we ended up with. We can pull a really similar trick for the right-hand side as well. So if I wanted to look at the limit as x approaches 1 from the right-hand side of our function, and again, we can use the simplified version of our function, 1 over x minus 1. Here again, I might take a number that's very close to 1 on this time the right-hand side. So I might take, how about x equals positive 1.1? We'll plug that into our function. We'll see if we get a positive or a negative number. So if I do that, I'm going to have 1 divided by 1.1 minus 1. 1, my numerator, that's a positive number, so we're just going to put a plus sign there. When I take 1.1 minus 1, I subtract those two numbers. I'm also going to end up with a positive number. And here, when I take a positive number divided by a positive number, I'm going to get back another positive number. So that means that the right-hand limit is positive infinity. So as far as what we need to give for our answers then, we said we have a vertical asymptote at x equals 1, a hole at x equals 3, the limit as x approaches as x approaches 1 from the left-hand side of f of x is equal to negative infinity, and the limit as x approaches 1 from the right-hand side of our function is positive infinity. That's what we're looking for here. We didn't have to say anything about our function at the hole because it only said at vertical asymptotes we want to evaluate the limits. So here's everything that we need. And we can use this idea of taking an x value that's close to the x value that we're approaching and plug it in. We can use that for any infinite limit or any vertical asymptote. I think it's the most efficient way to evaluate vertical asymptotes, as it makes those problems a whole lot easier. Let's take a look at one more here. Here's g of x equals x squared plus 9x plus 20 divided by x squared plus 3x minus 10. I would encourage you to pause the video for a moment and try this problem out on your own. See if you can find those zeros of the denominator, identify whether we have a whole or vertical asymptote at those zeros, and then for any vertical asymptotes, look at what is the left-hand limit, what is the right-hand limit. Look at the example we just did before this if you need a reference point, if you need to go back and check at any point in time. Hopefully you've had time to try that problem out. Let's go ahead and check our answers now. So again, I'm going to start this problem by factoring anywhere that I can. In my numerator, I should have x plus 5 times x plus 4. And in my denominator, I should have x plus 5 times x minus 2. And we've got that common factor of x minus 5. That's really nice that we can cancel that. We're left with x plus 4 over x minus 2. So we know any canceled factors, we need to take those and set them equal to 0. So that means that we're going to have a whole at x equals negative 5. So we've got a whole at x equals negative 5. Any factors that we cannot cancel or are left over with, we're still going to take those and set them equal to 0. but instead of having a hole, we are going to have a vertical asymptote. So this time we've got a vertical asymptote at x equals 2. So we don't need to do anything with the hole. We do want to evaluate the left and the right-hand limits at our vertical asymptote. So let's do that. Let's look at the left-hand limit first. Limit as x approaches 2. And again, we can use that simplified version of our function, x plus 4 over x minus 2. Now again, if we try and plug x equals 2 in, we're going to get 0 in the denominator, and that doesn't really tell us anything. But we know we've got a vertical asymptote, so we know that our answer is either positive infinity or negative infinity. We just got to figure out the sign. So because we're doing a left-handed limit, and I forgot to say we're doing a left-handed limit here, I'm going to take a number that's close to 2 on the left-hand side. So I might take x equals, how about 1.9? I'm going to plug that into my function and see what we get. So if I take 1.9 plus 4 divided by 1.9 minus 2, it's only the signs that I care about here. So if I look at my numerator and say 1.9 plus 4, if I add those two positive numbers, I know I'm going to get back another positive number. You can figure out the exact number if you want, but for us right now, it's really just the sign that matters. In the denominator, 1.9 minus 2, when I subtract those two, I'm going to end up with a negative. So I have a positive number divided by a negative number would give me a negative number. So that means that for this left-hand limit, this must approach negative infinity. For the right-hand side, we'll do something very similar. So we would like to find a limit as x approaches 2 from the right-hand side of x plus 4 over x minus 2. The only thing that's going to change is we're going to take a number this time on the right-hand side of 2. So how about x equals 2.1? So if I plug that into my function, 2.1 plus 4 divided by 2.1 minus 2, 2.1 plus 4 for my numerator is going to be some positive number. And 2.1 minus 2, when I subtract those two, I'm going to end up with another positive number. So here I've got a positive divided by a positive, which will give me a positive number back. And that means that my right-sided limit is positive infinity. So we have the left-sided limit here at 2 is negative infinity, and the right-sided limit at 2 is positive infinity. We know we have a vertical asymptote at x equals 2, and we have a hole at x equals -5.